Okay, hi everybody. Welcome back to Artificial Intelligence. As I mentioned yesterday already, today we're talking about inference and first order logic. And of course, because we just have a 45-minute lecture today, we're not finishing, but we'll see already very interesting results today. So first of all, I'm going to present to you how we can reduce inference and first order logic to propositional inference so that we can apply the methods we already know from propositional logic. And however, this can cause, the effect of this can be that we have a lot of additional statements that we need, and this can be very inefficient. So that's why we're going to use unification and lifting so that we can use the rules that we've learned for propositional logic also directly to first order logic sentences. And this is apparent in the next part where we are looking at forward chaining, because forward chaining we've already performed for propositional logic, and because we can lift Modus Ponens, we're then also able to use forward chaining for first order logic. And the same for backward chaining, because they use the same proof rule. They both use Modus Ponens, but just in different directions. And then we're also going to lift the resolution rule, so we can apply resolution to first order logic. And all of that can be found in the section Inference and First Order Logic in our AI book. Also, because there was some interest yesterday, I uploaded the link to the article I was referring to, where the authors argued that you also need logics for general artificial intelligence. Maybe I can just show you quickly. Now we have this new section for interested students, and the article is called "Why is AI so dumb?" And it's really a nice read. So over the weekend, if you want to have something nice to read, I can recommend this magazine. I mean, it's not one article. There are several articles about AI, so this was a special issue about AI. And I think most of you anyways know IEEE Spectrum. Okay. And there's also a link to an interview with Stuart Russell, who is one of the authors of our the book that we use in our lecture. Okay. And of course, both things are not relevant for the exam, just to be clear. Oh, I've just realized I haven't used the slides with the overlay. So let me just change this quickly. We always have like a handout version and the version for the lecture. Okay. So what are the learning outcomes of today's lecture? You can eliminate existential and universal quantifiers, which is then required, as I mentioned, to translate everything to propositional logic sentences. You can understand the problem of propositionalization, which is, as I mentioned, the idea that we convert first order logic sentences into propositional logic sentences. Then as I said, we will realize that this is not very efficient. So we will lift these rules that we have already seen. And for instance, we will have generalized modus ponens and unification techniques. That makes it then possible to use forward and backward chaining. And you understand when to use forward and backward chaining. Actually, the reasons are the same as for propositional logic. And you can transform any first order logic sentence into conjunctive normal form. This is then required to use the lifted resolution rules. Okay. So let's start with removing quantifiers in first order logic, because of course there are no quantifiers in propositional logic, and if you want to convert it, then we have to get rid of them, obviously. And so this will, as I mentioned, naturally lead to this propositional inference rules, which we already know, and we will start with eliminating the universal quantifiers and then existential quantifiers, and then discuss the result. Okay, so let's start with removing universal quantifiers. So we can just have a simple proof rule where we say, okay, we have a statement that is true for all x's. So if we replace x with some constant, let's say c, then the sentence where we replace x with a constant c is still valid, because if it's valid for all x, then for particular constant, this should also be valid. And instead of C, you can also use John or Richard or father of John. So the rule is actually very simple. We can just substitute any we can substitute any variable by a ground term. So a ground term is a term without variables. So here we had the original rule was for all v, some statement alpha holds. And then we will replace this formula with, or we can infer from this, not replace, we can infer from this formula a new formula where we substitute v with the ground term g in the statement alpha. And this is, of course, a true statement. So I can replace x with anything. It's always true because it holds for all x's. So how this substitution is meant, I mean, it's as you know, it's like a typical substitution in mathematics. But here's an example. So we can substitute, for instance, here x by John, or x by Richard, or x by father of John. And then we obtain these three sentences that are all true because this sentence is also true. So we can just replace the x or the variables with constants and obtain new sentences which are all true. Okay, now let's talk about existential instantiation. So what is essentially the difference? What do you think is the difference if we have to get rid, or maybe is of existential quantification instead of universal quantification? Do we have to take care of something when we do the substitution? So essentially, we can only we can do the substitution only once, because if existential quantification could only be that there's one case where for which the formula holds. So what we do is we have v is existentially quantified, and so there exists a v such that alpha holds. And what we can do, we can replace the v with some constant k, but we can only do this once. And the k is, you can only replace it with something that is not part of the knowledge base. So it has to be a new symbol. That's very important. So for instance, here we have the existing x, where x is a crown and it's on the head of John. And I can just introduce a new constant C1. And then I can say, okay, C1 is a crown and it's on the head of John. So this new constant is also called a Skolem constant. So we will use this term later on again. So here's another example for mathematics. So you say, okay, there exists an x such that if I compute the derivative of x to the power of y with respect to y, then I obtain x to the power of y again. So we could give it a new name. And the new name is E, and E is called the Euler's number. It has to be a different symbol, so we can call it pi, because pi is already used for circles. So you see how this works, and of course you could have given it a completely different name if it hasn't been used in mathematics already. Then this is also fine. Okay. So now let's talk about what we can do without changing the knowledge base. So in universal instantiation, we can apply these replacements several times to add sentences. And the new knowledge base is logically equivalent to the old when performing all possible substitutions that are possible given the knowledge base and deleting the quantified sentence. So we can remove the sentence for all x, king x, and greedy x implies evil x if we have made all possible replacements for x given a knowledge base, or we just keep the sentence and just add a few sentences. So this is also fine. Or adding new sentences and keeping the quantified sentence. So for existential instantiation, we can only apply this once to replace the existential sentence. So once we've made this replacement here, so the substitution where we replaced x by C1, the sentence, the existent x, crown x on and on head of John, has to be removed, because it could be that just C1 is the only possible solution. And yeah, then we have replaced it already. And if we keep this, it implies that there might be a second case where this holds. So that means also the new knowledge base is not equivalent to the old one, because it could have been that there are maybe two crowns for which this holds, but we have just made one replacement. However, what we have is that the new knowledge base is satisfiable if and only if the old knowledge base was satisfiable. So for proving things, it doesn't really matter. However, the knowledge base is not equivalent. So, okay. So here's an example. Suppose we have this knowledge base where we say, okay, we have for all x, and x, if x is a king and x is greedy, that implies that x is evil. Then we know that John is a king, John is greedy, and Richard is the brother of John. And now if we can instantiate, make this universal instantiation for all possible x's of this database, we obtain the following. We can replace x with John, x with Richard, and that's the only two possibilities, because there are no other people involved or no other objects than Richard and John. And then you obtain this new knowledge base. And this is a knowledge base which is propositionalized. So you can say, for instance, King John refers, as I mentioned, this is a term, but the term in the end just refers to an object. So all these objects can be replaced by propositional symbols, and then you have just a propositional logic, a set of propositional logic formulas. So for instance, the propositional symbols then would be King John, greedy John, evil John, King Richard, and so on. And because we've used all possible ways, we could remove this quantified sentence here. Okay. So now we claim that every first order logic knowledge base can be propositionalized to preserve entailment. So the idea is, as I've shown to you already, we propositionalize the knowledge base, and then we use the inference rules that we already know from propositional logic. For instance, we could apply resolution and then obtain the result. There's just one problem, and that is because first order logic allows one to use function symbols. So we can have like this indefinite function calls, so that we have, okay, father of the father of the father of John, or we can add several fathers here. This can go on forever. So that means we don't have then an infinite number of possible propositional symbols. So there's this theorem from Herbert from 1930. So this goes back quite some time, which says that if a sentence alpha is entailed by a first order logic knowledge base, so if the sentence is true, then it can also be entailed by a finite subset of the propositional knowledge base. So that means you don't have this infinite sequence here. That's good news. However, there's the question is what happens if the sentence alpha cannot be entailed? So if alpha is not true. Okay, before I go there, just one more comment. So what we can do, we can use something similar that we used already in iterative deepening search. We can say, okay, we just consider a depth of function calls of depth 0 first, and then increase the depth from step to step. And then at some point, if alpha is true, we will be able to prove that alpha is true. However, if alpha is not entailed, cannot be entailed, or if alpha simply is not true, we are looping here forever. So we don't find this finite depth. So then there was a follow-up theorem from Turing and Church. These have been invented in parallel, which said that entailment in first-order logic is semi-decidable. Why? Because of if it's true, if alpha is true, then we can find it, and alpha is not true, we cannot prove it, or we cannot we cannot decide and say, okay, after a finite number of iterations, we can prove that alpha is not true. So here it's, again, algorithms exist returning yes to every entailed sentence. So if this is true, but no algorithm exists that can also return no to every non-entailed sentence. So that's why it's just decidable in one direction. Okay. So there are, besides this theoretical problem, there are some additional issues, of course. As I mentioned, you might have to create a lot of sentences. So let's look at this database here, where for X, King X and greedy X implies evil X. John is a king, and everything is greedy, and Richard is the brother of John. So if you want to show that John is evil, then it's quite obvious that this is the case, because we could replace X with John. We need then that John is a king, which is already stated here, and everything is anyways greedy, which is stated here, and that's why we can imply that John is evil. However, if you would use propositionalization, then we would produce a lot of facts such as Richard is greedy, which are completely irrelevant. And can anybody think of how many kind of replacements we might have to do in the worst case? Just think of the predicates, right? So let's say if a predicate X and Y, so if X has n possibilities and Y has n possibilities, we will have n squared possibilities. So depending on the arity of the predicates, we have it's exponential number of arguments, and then we have also a lot of potential predicates. So if we have, as I said, the k-array predicates and n constants, we have n to the power of k instantiations for one predicate, and if you have p predicates, then it's p times this number. So this can be really large, and this is only the case when we have no function symbols. So for function symbols, it gets even worse, because functions can call functions, and this can go on indefinitely, of course. So which is written here, and that's why we would like to have a different solution, and that is that we want to get rid of this propositionalization, and we would like to have directly inference rules for first-order logic sentences. So to infer that John is evil using this knowledge base, we see that this is actually not a difficult task. So if we replace X with John, which is possible using universal instantiation, we have King John and greedy John. These two are true based on the knowledge base. So because the premises are true, then the conclusion is true. And because we replaced X with John, we have proven that John is evil. So basically, we have used a generalized form of modus ponens here. So where we replaced X with John. And yeah, this is then called generalized modus ponens. So how does it look like? We have several facts, P1 prime up to Pn prime. And then we have an implication with several premises, P1 up to Pn, which imply Q. And if we can find a substitution such that P1 matches with P1 prime, P2 matches with P2 prime, and so on, then we can infer Q. But of course, because we have used these replacements, we also have to apply this replacement to Q. So we also have to use the same substitutions, theta, and apply them to Q. And here is then the inference rule. So after we have, we made these statements identical using substitutions, we can infer Q, but we then have to, of course, apply the substitution rule again. So here's an example. It's almost the same as on the previous slide. So for all x, king x and greedy x implies evil x. John is a king and everybody is greedy, or everything is greedy. So now what we have is, okay, we have king x here and we have king John here. Maybe I can use my pen and I can show this a little bit better. Okay, so this here matches this. But of course, in order to make this match, we have to use this replacement, and we have to replace x with John. And I can use maybe another color. First, I think I have to go here. Okay, so then we have greedy x here, and we have greedy y here. But we can replace y with John. So then we have here greedy John, and greedy x is already greedy John because we already said x is replaced with John. And then because of that, we can follow evil x, and x is replaced with John. So then we know that after replacement, we have evil John, and this is what we wanted to show. And evil John is nothing else like applying the substitution rules. These are the substitution rules to Q, and Q in our case is evil x. So after substitution, we have evil John. It's just a view. Yeah, I think I have to get rid of this. Then I can do this again. Yeah. Okay. Okay, so we will see many examples. Okay, Adrian just replied. Somebody just wanted to see an example, so this is one of the examples. Okay, so now we can also prove the soundness of this rule. This is not relevant for the exam, but it's also very simple proof. That's why I would like to show it. So what we wanted to show is that if we have P1 prime up to Pn prime given, and this implication here, then we can use the substitution. We can entail that after using the substitution rules theta, we can entail Q. Okay, so and of this, of course, can only be done if we can find a substitution such that the Pi primes match with the Pi's. Yeah, so for any sentence P, we have that P. Yeah, so as an auxiliary lemma, which we will use, is that for any sentence P, of course, when we use a substitution, then the sentence, of course, still holds after the substitution by the rule of universal instantiation. Okay. So because a substitution never hurts, what we can do is we can take the implication from here. So maybe I use again the pen. Maybe then it's a little bit easier. So basically, we are using this implication here. And now every variable is replaced using the substitution rule. So this doesn't hurt. And that is okay because of this rule. So replacement doesn't change anything. So next, what we're going to do is we are looking at this part. Again, we use the substitution. So we can rewrite this instead of having commas. You can just write the end symbol. It's the same thing. And then we're using, again, this rule for substitutions. So this is replaced with this. This is replaced with this, and so on. That's also very simple. And finally, we put everything together. this is given, that we can find the substitution. And by using these two steps from before, step 1 and 2, we can just use ordinary modus ponens, because what we have is, we have that the premise is true, which is here. And because that is the case, we can make this conclusion that this is true. And this is exactly what we wanted to show. So this was then in the end just a standard modus ponens. Okay. So now we have shown that this lifted version is correct. So one aspect that we haven't talked too much about today is how we can find these substitutions. And there is a way to do this automatically called unification. So you can unify, there's an algorithm called unify, which performs this automatically. But we will just do this by hand for now. And this will return this replacements theta, such that here the P's and the Q's are matching in the end. So here's some examples. We have John knows X and John knows Jane. So what replacement do we need? Maybe if you like, you can write it in the chat. Yes, we have to replace X with Jane. So this was easy one. So the next one, we have John knows X and Y knows Elizabeth. So what replacements do we need? Again, please type it in the chat. Yes, we have Y John and X Elizabeth. Sorry, X Elizabeth and Y John. Yeah, I said it correct, but just in a different order. And next, now this is the next one. So Y John is obvious. What else do we need besides replacing Y with John? Yes, X with mother of John. So Y John and X with mother of John. Okay, now a fourth one. What would be the solution of this? Yes, error, that's not possible, correct. The problem why this fails is because we're using the same variable X here. So what the intention probably was is that John knows X and somebody else knows Elizabeth, but this X is reused twice. So what you have to do is maybe you should replace X with Y or Z or with something else. And we can automate this as well. So we can use some algorithm that always creates a new variable, which is called standardize apart. So we could use, for instance, X17 Elizabeth, and then there is no danger that this wouldn't work, and then we would find a unified replacement. Okay, so now we have a few further questions using TweetBack. So the first one is we have parents. So X. So the parents of X are father X and mother Bill, and the parents of Bill are father of Bill and Y. So which substitutions do you have to make? Is A correct or is B correct?
For now, all participants chooses B. Oh no,
Yeah,
97%.
Yeah, that's correct, because Z is nowhere else, so that's quite easy. So second one, parents of X, the parents of X are father X and mother Bill, and the parents of Bill are father Y and Z. So what would be here? what would the correct replacement here?
Now about 80% chooses A.
Yes, correct. I mean, you can easily see that B is incorrect because we replace X with Bill and X with Y, and that's not possible. We cannot replace the same variable with two different things. So A is certainly the correct one. Very good.
Perhaps
Yeah.
there are some people who have trouble on slide 14 with the other examples of unification. So I think you explained the first one with X substituted by Jane, but I think they have trouble with the other ones.
Okay. Yeah, the good thing about substitution is you just have to insert it. So if you replace X with Elizabeth, then you have John knows Elizabeth. And if you replace Y with John, then you have John knows Elizabeth. So then both statements are the same. So after inserting everything, both sides should be the same. The same here, like if you replace X here, where my mouse pointer is, then you have mother of John, then you have John knows the mother of John. I mean, you should know your mother. It's kind of silly, but yeah. And here we have then Y is replaced with John, and then you have John knows the mother of John, because here the Y also is replaced with John. That's easy. That's always easy to verify. The harder part is finding these replacements. And there is, as I said in the book, there is a unification algorithm. We didn't include it in these slides because we already introduced a lot of algorithms. And because, yeah, for the examples that we need for the exam or for the exercise, it's an overkill to use this algorithm. This is only important if you have larger knowledge bases. That's why we excluded it, so that we are not overwhelming you with too many algorithms in this lecture. So
another question that came up a couple of times is on this next slide for the tweetback question B. If it would make a difference if you took the substitution Y substituted by X and not X by Y.
Yes, so it's always the left one is replaced by the right one. This is what this kind of the notation that we use. So the order in which you do the substitutions, that's also written here, doesn't matter, but you always have to replace the left one with the right one. Okay. Yeah, okay. So there was just another question. Why does the second example doesn't result in Y father, Y set? Because it is Y bill. So maybe I can quickly explain the right answer. So X is replaced with Bill. So then we have Bill, father of Bill, and we have mother of Bill. And here we have Bill, father of, because we replace Y with Bill, father of Bill, and then mother of Bill. So then both are the same. That's why A is correct. And B is already not correct because you're replacing X with two different things, which is not allowed. You can only replace one thing with another thing, but not have two possibilities for one variable. Okay. So there are now some more interesting aspects regarding unification. So we could unify John knows X and Y knows Z, but there's more than one possibility. So for instance, we could choose Y is replaced with John and X is replaced with Z, or Y is replaced with John, X is replaced with John, and Z is replaced with John. So maybe that's the first one is solution A, and the second one is solution B. Maybe you can have a quick feedback question, what people prefer, A or B.
So about 60% chooses B.
Okay, so let's discuss this. So the first one is more general. Why is the first one more general? So then we would have John knows Z and John knows Z. And if you would do another substitution, then we could also replace, let's say, Z with John, and then we have John knows John and John knows John. The only thing is, like, John knows John, so I know myself, essentially, is not so exciting. But that John can know any person, and this is still okay, is a more general statement. So it's usually you want to keep everything as general as possible. And that's why this one, the first one, is usually preferred, because if you don't keep it general, you might not have all the facts or all the knowledge that you need to prove a certain thing. You can always make it more concrete anyways. That's easy to do by a substitution, but you want to keep it open as long as possible. And there exists this algorithm for most general unifier, which is in the AI book. Maybe you just have to check whether it's still figure 1 in like in the 4th edition. It was that the case in the 3rd edition. If you see that this is not correct anymore, just let us know. But that's what you usually want to have. Yes, here's also the comment: if variables are replaced by variables like x with z, then yeah, the left's always replaced with by the right one. Maybe we should introduce this earlier in the we should update the slides and say earlier that we are always doing it this way. Maybe Adrian, we can discuss after the lecture. Okay. Good. So now let's talk about horn clauses. Why? Because we have seen when you have horn clauses in propositional logic, we can use modus ponens and use forward or backward chaining to prove statements. And in a propositional logic, we had that a horn clause is a horn clause if you have a propositional symbol or a conjunction of symbols imply another symbol. So the difference for first order logic horn clause is very simple. You just allow additionally that all variables are universally quantified. So universal quantification is the only quantification. So implicitly you always have for all x or for all y. If x or y appear in or z or any variable appears, so any variable occurrence means that it's universally quantified. And if it would be existentially quantified, it would not be a first order horn clause. Okay, so the main idea now is to use this lifted modus ponens and apply forward chaining exactly as we have seen it for propositional logic. So this process repeats until you cannot find any new facts, or you can prove that the goal. And the fact is not new if just renaming would produce the old fact. So this is, of course, this problem you don't have if you have just propositional symbols. But if you have variables and one variable is x and the other variable is y, then these two statements, of course, are identical because I can just rewrite the variable here. And then it's not a new statement. Then we basically have shown that if you cannot prove the statement we want to prove, and we cannot produce any new facts based on because we could just replace existing facts or rename existing facts, then we have shown that this cannot be proven. What we also will use is to standardize apart, so that we are making sure that unification always works and is not failing because we haven't renamed any variables. So we want to avoid this situation that we had before, where we had, okay, John knows X and X knows Elizabeth, but the two are actually, X's should be different here. When we use standardize apart, and then we would automatically find a new variable name. Okay, so this is the forward chaining algorithm. It's fairly simple. Initially, the set of new statements is empty. Oh, sorry. So initially this is empty, and also we repeat forward chaining as long as until new is empty, until we don't find any new statement anymore. So for each sentence, we use this standardized apart. And then for each unification, or for each substitution, which makes it possible that the premises that we need for this implication match the facts in a knowledge base. If we find such a unification, then we can use modus ponens and we can conclude Q. And again, we have to perform all the possible substitutions on Q to obtain Q prime. So if Q prime is not a renaming of an existing sentence that is already in a knowledge base, then we add Q prime to the set of new sentences. And then we unify Q prime with alpha was the thing we wanted to prove. And if this is not a fail, then we have proven basically that alpha is correct. And otherwise, after this inner loop, we return back to the outer loop and add all the new statements we have found to the knowledge base and continue until we don't find any new sentences. And then we have proven that alpha is not true, or otherwise we have proven alpha to be true, and then of course we terminate. And so somebody asked what KB means. KB stands for knowledge base. Okay, so let's look at an example. Yeah, so this is about criminal West. So you can, yeah, this is a typical criminal case. I mean, if you read it as a human, it's obvious, but we will prove this automatically. And if you would have a much more complicated criminal case, then you can, you can also solve it. Also, there is like this board game where you also have to figure out who has killed somebody with different rooms and different objects. What's it called again? It's very famous. Yeah, Cluedo. So if somebody wants, you can use our algorithm and maybe put them on a smartphone so that nobody sees it, and then win every Cluedo game if you are interested. Or Clue in English. Yeah, Clue is the English version. Okay. So did I already read this? I don't know. I forgot if I read it already. So the law says that it is a crime for an American to, no, I think I didn't read it. So the law says that it is a crime for an American to sell weapons to hostile nations. The country no, an enemy of America, has some missiles, and all of its missiles were sold to it by Colonel West, who is American. So obviously, Colonel West is a criminal. Now we have to prove that. The only thing is that we're out of time. So we can continue formalizing these facts that we have given, and then prove this automatically that he's guilty. Okay, good. So thanks for joining today. Yes, wish you a nice weekend and a nice remaining exercise. And who's taking over? Or
I will be taking over. Can you hear me? Yes. Okay.
Good.
So then the exercise will start in 2 to 3 minutes approximately.
Okay. Yes. Bye.
Bye-bye. Yeah, good. The recording has started, so I hope you can hear me all clearly. If not, then just write in the chat. So yeah, welcome everybody, and hello from my side to this exercise session again this Friday. So Dawi has already shared the tweetback link in the chat again, which you can use for any questions. And yeah, then we can, I guess, start with the exercise. So yeah, today's exercise session will be on constraint satisfaction problems. So basically what we've covered in lecture 5. And since this lecture again was a few weeks ago, we'll just, as always, start with a quick recap of the lecture content. So in constraint satisfaction problems, what are we dealing with? We're basically dealing with a problem that's defined as a tuple of 3 components. And those 3 components are X, which represents a set of variables, D, which represents a set of domain values, And domain values in this case means that each domain DI consists of the allowable values. So basically D1 would tell us the allowable values for X1. So all the values that X1 may have. And then also for DN would tell us the same thing for XN. And then finally, or most importantly, we have a set of constraints represented as, or typically we call that C, or we use the letter C for that. And the set of constraints basically gives us some kind of relationship between those variables and tells us, for example, how one variable how the value from one variable should behave if we have assigned another variable. And these set of constraints can be either unary, this means they're involving one variable. They can be binary, this means they involve two variables. This is the most typical case we will look at. And they can also be higher order constraints, and then we call them n-ary constraints. Now, the goal of a CSP is to say, okay, we want to assign a value to each variable such that all constraints are satisfied. So basically, we want each variable X to have a value in the end, and we want all constraints C to be satisfied. And then we say this is a valid solution for our problem. Okay, so the way we solve such a problem is with a technique or with an algorithm that we call backtracking search, which is more or less based on the search algorithm that we had on the depth-first search algorithm that we've covered a few exercise sessions ago. And this is the algorithm that we've also had on the lecture slides. We're not going to go through that in detail now. So it's just here to show the three most important components that we're also going to take a look at in this exercise. So the first one is called variable selection. This is something that's done here in this line, select unassigned variables. So there we try to answer the question, which variable do we want to assign next? Then value selection, which is done in this line here. So then this is basically where we say once we have selected a variable, which values and in which order do we want to try out the values for this variable. And the third one is then called inference, which is done in this line here. So then this is a step that we're going to take a look at later on. So this is try to infer solutions all before we continue the search, but we'll take a look at that in a minute. So yeah, these are the three most important heuristics that we're taking a look at. And we're going to go a little more in detail now on the next slide. So for the first one, variable selection, we learned two important heuristics in the lecture, which were minimum remaining values. So in this, if we use this strategy, we say, okay, we choose the variable with the fewest possible values first. One could also say the variable with the smallest domain. Smallest domain. Yeah. Then the next heuristic that we've learned for variable selection is the degree heuristic. So the degree heuristic says that we choose the variable that is involved in the largest number of constraints, so the largest number of constraints on other unassigned variables. This is what we call also the highest degree. So the degree of a variable is basically the number of constraints this variable is involved in. So for value selection, we want to answer the question, in what order should values be tried if you have selected a variable already? And there we learned one important strategy, which is called least constraining value strategy or heuristic. And in this heuristic, we say we choose the value that rules out the fewest choices for neighboring values in the constraint graph. What that exactly means, we'll see then when we take a look at the exercise 3.2 or the problem 3.2, there you'll get an example or a feeling for how that actually is applied for a constraint satisfaction problem. Okay, and then the third thing I want to just address before we jump into the problems is inference and arc consistency. So arc consistency is an important concept used in constraint satisfaction problems, and it's basically describes how domains of variables that are involved in a constraint have to be, have to look like to be arc consistent. So we define for two variables xi and xj, we define that they are arc consistent if for every value in domain di, there exists a value in domain dj, which satisfies the constraint between those values. And this constraint we also call arc. So as an example, we've also had this example in the lecture. We use the constraint y equals x squared, and we say we have domains dx like this, and we have a domain dy like that. And then we can say that x is arc consistent with y. Why can we say that? So if you take a look, at the domains, so we see that for every value that we have here, I'm sorry, yeah, good. So for every value that we have here, we have a corresponding value in dy that satisfies the constraint. For example, if you choose value d2 in x, then dy has to be 4, or y has to be 4, which is in the domain of y. And this is valid for every value that we have here in the domain of dx. Now, the other way around, this arc consistency isn't true. So if we say y has to be arc consistent with x, this is not true currently. Why is that not true? Because if we have, for example, if we choose y as 5, then our x value would have to be the square root of 5 to satisfy this constraint. And as we can see, the square root of 5 is not part of the domain of dx, and that's why we can't say that y is arc consistent with x. So this is very important when looking at arc consistency, is that the direction of this arc matters. Okay, so then we have two inference techniques that we learned, which we're also going to take a look at later on. So we have forward checking and arc consistency algorithm. So in forward checking, we remove the inconsistent values of the neighboring variables for a certain variable that we just assigned. And in arc consistency algorithm, we remove the inconsistent values of all variables in the graph, so not only the neighboring values. So this is kind of like an extension or an improvement of forward checking, and that's something we're gonna also see later on, how that affects the search process of a constraint satisfaction problem. Okay, good. So after we have defined these basic concepts now and revised them, let's just start with the first problem. And in the first problem, we want to try to look at the constraints, or a higher order constraints, a little more, and see how one can transform them into binary constraints. So we have a CSP, which is defined here, and we have our variables, our domain, and our constraints. In this case, we use the letter E for constraints and not C, because we don't want to have any conflicts with our variable C. So that's why we just say E are our constraints. Yeah, then each variable has a domain, so domain A, B, C. And for example, they could be something like 0 to 9. The domain, or the actual domain, is not important for this problem in this case. Yeah, so the first problem is, we want to draw the constraint hypergraph for the CSP, and we say in the problem, this is not written on the slide now, but in the problem PDF that I've uploaded, or that we uploaded, we say that we want to use a circle for the variables, and we want to use a square to describe the constraint. So how is this the constraint hypergraph going to look? We have to take a look at the constraint again, and we see that we have a constraint. We have only one constraint, which involves the three variables A, B, C, and the constraint is that A plus B has to be equal to C. So we have three variables involved in one constraint. So in the end, our constraint hypergraph is going to look something like that. We have variable A, represented as circles, variable B, and variable C. And they're all connected with one constraint here, which is basically the constraint that we have given here on this slide, A plus B equals C. Okay, somebody asked, what is a constraint hypergraph? So a constraint hypergraph is basically just a visualization of what we see here on this slide. So it's just a visualization where we visualize the variables and the constraints, and we just show what's written here in a kind of a graph structure or a graph way, which is in most cases simpler to read for us than in such a, yeah, if we describe it just as variables. Somebody asked, what are X, D, and E again? So X are the variables, D are the domains of those variables, and E are the constraints in our problem. Yeah, this is what I showed basically on the first slide of the recap. Okay. Yeah, somebody asked, is there a standard format for drawing the hypergraph? Yeah, I'm not quite sure if this is a standard format. So it's a typical format to draw it like that. I don't know if it's standardized or anything. So in this lecture, we draw them like we drew it here in this case. Okay. All right, then, yeah, okay, the square, somebody asked what the square means. So the square, I can write it down. So this are the variables. And this are the constraints. Yeah, exactly. Okay, so what we're going to do now is we want to eliminate the higher order constraint in E. So we see that if we go back to the original problem, that we have a higher order constraint here. Higher order means it involves 3 variables. So as I said in the beginning, we can have constraints that involve only 1 variable. We have constraints that involve 2 variables. And then we have higher order constraints. That means they involve 3 or more variables. And typically, a constraint satisfaction problem is easier to solve if it only involves, for example, binary constraints, meaning constraints with 2 variables. So that's what we want to do here in this case. So we go to problem 1312, and we say we want to transform our CSP into something like that by introducing a new variable set z. So we say we want to replace the constraint node, so the square we have earlier, into a new variable. And we have to somehow say what is the domain for the new variable and what is the new constraint set. Okay, so the new graph looks something like this. So we want to have a graph that looks something like that. A, B, C. And then instead of the constraint, we have a new variable z. And now we have to somehow say, how does this variable z look like, or what is the domain of this variable z? So the domain of this variable z is going to look something like that. So in this case, we say that z, I can write it here, z has to be a 3-tuple. What that means, I'll show you in a minute. So 3-tuple basically means that z is not a single variable, but it's kind of made up of those. Oh, sorry, this is too small. But it's somehow a variable that looks like that. Yeah. So a variable that's made up of 3 components, basically a 3-tuple. Yeah, so that's basically the variable z. And now we have to say what is the domain of z. So we say that each component of z has to be within the domain of the other variables. So I'm going to write it down and then I'm going to explain it to you in a minute. So z1 has to be within the domain of A. z2 has to be within the domain of B. And z3 has to be within the domain of C. Okay. So this is a kind of a technique that we're going to introduce now to say that if we have a higher order constraint, we want to reduce the order of the constraint into a lower order, or a binary constraint, for example. And the way we do that is if we say, okay, this variable is connected to, the variable z is connected to 3 other variables, a, b, c, then we represent this variable as a 3-tuple, so z1, z2, z3, and each component of z has to be within the domain of the other respective variables, just like it's written here. Okay, so then the question was, what is the new constraint set stroke? So we can write it up maybe like this. We can say we have a new constraint satisfaction problem. The new constraint satisfaction problem looks something like that. So we have a new set of variables. So compared to the previous problem, I can go back. We have added variable z, right? We have a new set of domains. So we have domain from A. We have the domain from B. Domain from C, and the domain from Z. Yeah. And then we have a new set of constraints, which is basically looks the following. So we have the first constraint. I'm going to write it in short form. Yeah, I'm going to write it in short form. So it's going to look like that. I'm going to explain it in a minute, what that means. So now this Fst operator I wrote here, basically what it does, it retrieves the first value from the variable z. So basically this here corresponds to z1. So that's what this operator does. This is something we've introduced now to represent this constraint. So what we say, if we have a tuple and we use Fst, so first of the tuple z, then we're going to get the value z1. So yeah, and we said since z1 has to be within the domain of A, we can write this constraint here like that. Okay. Then the second one is in principle similar. So this SND operator, it does, I can maybe color code it a bit. So SND operator gets the second value. So we get this here, Z2 element of domain B, and then we have equivalently for C, the third operator, which gets C, yeah. And then we have to pay attention. I'll also color code this, so then it's clear, like that. And then we have the third operator, which, the third constraint, the fourth constraint. And because if we go back to our original problem, we saw that our original constraint had this here. A plus B has to be C. This is our higher order constraint. And now what we have to do is we have to still write this additionally into our constraint set. And in this case, it's pretty simple because we say that our constraint is just that. So, and since Z1 is always within A and Z2 is always within B and Z3 is always within domain C, we can say that we can replace this constraint that we had earlier with this type of constraint, which is Z1 plus Z2 equals Z3. Yeah. So this might seem a little abstract now, but I think in the next problem, when we do that, it's going to get a little more clear why we do that. So we're going to just remember this and continue with the next problem. And in this problem, we say we want to modify this CSP stroke that we had here. So this is basically this here. We want to modify it such that it only contains binary constraints. So as we see now, we have 3 binary constraints. So the binary constraints are this one, and this one. Binary means they involve 2 variables. So this constraint involves Z and A, this constraint involves Z and B. And we have 1 unary constraint, which is this one. So this involves only variable Z. And now we say we want to modify it such that that this constraint set only includes binary constraints. Okay, so how are we going to do that? So what we have to do is we have to somehow take this unary constraint here and include it into the domain of Z such that it can be removed from the constraints and it's considered directly within the domain. Yes, one more important thing. Somebody asked if there should be a square constraint node in each arc of the new graph. Yes, there should be. It's just I drew this. We drew this constraint graph beforehand, before actually defining the constraints. So this was just to get an idea what we're doing. So essentially, in the solution afterwards, in the new CSP, we would have some kind of constraints here, obviously in between. Yeah. But good point. Thank you for noticing that. Okay, so we said we have to change the domain of Z such that we can include the unary constraint directly. So what we're going to do, we're going to write how our constraint how our domain from Z looks like. So again, our variable Z is Z1, Z2, Z3. And now we said we want to consider this constraint here directly in the domain, and this is pretty simple to consider because we're just going to add it to the wait 1 second. Yeah, we're just going to add it to the domain. So we're going to say, okay, the variable Z consists of a tuple of 3 components, and we have the first condition is Z1 plus Z2 has to be Z3. and additionally, so this is the and operator, we have to say Z1 has to be in the domain of A. So that's just basically the three conditions that we had previously here. These three conditions that we had previously here have to be included. So Z1 has to be in the domain of A, Z2 has to be in the domain of B, and just going to write it in the next line, and Z3 has to be in the domain of C. Yeah, so this is our new domain that we have now. And now what we're going to do with this new domain, we're going to define our new constraint satisfaction problem, two-stroke here. So our new CSP stroke is going to look like that. So again, we have our variables, which are the same as previously. We have 4 variables now, C, that. We have our new domain, which is basically domain from A, domain from B. So for each variable, we have a domain and domain from Z. So this here now corresponds to this here, domain from Z. And yeah, finally, we have our new set of constraints. And now what we can see is that if we go back to the previous set of constraints, that we've actually transformed this constraint into a, or we've considered this constraint directly into the domain. So we don't have to consider it in the constraints anymore. And we are left with only these 3 constraints here. So our new set of constraints is going to look something like this. We have, again, the first operator from Z, which equals A. We have the second operator from Z, which has to be B. And the third operator from Z, which has to be C. Okay, and now what we can see is that our a new set of constraints only includes binary constraints. So I'm just going to write it here. These are only binary constraints. Yeah. So now what's important to note is that this problem that we've defined here, so this new CSP here, it's basically equivalent to the original CSP, so to the one that we've defined here in our problem. It's the same problem itself, only that we don't have a higher order constraint anymore, but we have binary constraints. Yeah, we only have binary constraints. And this simplifies our problem, our constraint satisfaction problem a lot. Yeah, so that's the point of, that's this thing that we wanted to show in this problem, that we can take a higher order constraint and turn it into binary constraints, and this simplifies our search problem than our constraint satisfaction problem a lot if we have simpler form of constraints. Okay, now I'm going to take a look at some questions. So aren't all okay, what was the question? Aren't the constraints already included in the domain Z? Let me see. I'm not quite sure to which one this refers to, probably to 3.1.3. Okay, here it's again, aren't all E2 stroke constraints considered in domain Z? Yeah. Okay. So I guess it's referring to that. Yeah, Z1 element domain A, Z2 element domain B. Let me check quickly. It's a good question. So I'm not quite sure exactly why that is the case. So I'll take that down, I'll note that down, and then I think I'll answer this question in Moodle. I would have to quickly think about that, why we consider So they are to some extent considered, but we still need them as constraints here. I'll take that down, this question. So thanks for the question, and I'll answer it on Moodle. Okay. All right. Yeah. Okay, yeah, I'll answer that on Moodle later on, then, so that we can continue with the exercise. All right. So now, this is just a summary from the previous two problems. So we said if we have any n-ary constraint, so any higher order constraint, how can we turn it into binary constraints? So the first step is that we have a constraint of order n. In the previous problem, it was order 3. We can represent this constraint of order n with a relation like that. So this has still order n. Now what we can do is we can replace the n-ary constraint by a new variable. And what's important is that this domain of this variable z is a n-tuple. So it has to be a tuple of the same order of what our constraint was. And then we can restrict this domain like we did in the problem 3.1.3. And then finally, we can introduce the new binary constraints to match the values of variable z. And for example, in this case, we said these are these constraints that take the first and second operator of the tuple, and we obtain the values of the neighboring values, basically. So in our example, it was values A, B, and C. Okay. Good. Then we should continue with the next problem, which is basically performing a backtracking search algorithm by hand. So yeah, we have a new constraint satisfaction problem. So this constraint satisfaction problem is modeled here directly as a graph. And in the in your PDF problem, in the exercise sheet, you've also had it where we write explicitly the variables x, t, and e. So variables, domains, and constraints. And here we have the same thing as a graph structure. So again, we use this notation that variables are represented as circles and constraints are represented as squares. And in this case, we also write the constraints and the domains of the variable here. So I can just write it out. So this is the domain, for example, of variable 1. And this is, for example, a constraint here. Okay. Now, in this case, we only have binary constraints. So as you can see, they only involve 2 variables at a time. And the first problem that we want to say is we want to sort the variables by domain size and by degree. So the first thing we're going to do is we're going to say, okay, we're going to sort them by domain size. So we're going to look domain size. And we're going to take a look and see that all variables have the same domain size. So as you can see, they're all have a domain of 3, of size 3. So we don't have to sort them. So we can say domain size is 3 for all variables vi in our graph. And the second thing we want to do is degree. So again, remember what degree means. So degree basically means in how many constraints a single variable is involved. So we can start with the highest. The highest is variable 3 because we see it's involved in 1, 2, 3, and 4 constraints. So you can write that down. So it's variable 3 has 4 constraints. Then we continue with the next. So it's basically variable 1 and 5. So we can see variable 1 is involved in 1, 2, and 3 constraints, and variable 5 also 1, 2, 3. So we can write down variable 1 and variable 5 involved in 3. And finally, we have variable 2 and 4. Variable 2 is involved in 1 and 2 constraints. Variable 4 also 1 and 2 constraints. And then we can say that variable 2 and variable 4 are involved in 2 constraints. So these are the degrees, and we have the domain size, which is 3 for all the variables. Okay. Good. Then in the next problem, we want to perform a backtracking search by hand. which means that we want to run basically this backtracking algorithm that I showed you and write down every step of that backtracking algorithm, of this backtracking search algorithm, and see what is the result that we get in the end when we solve this constraint satisfaction problem with this algorithm. Okay, as I mentioned before, we have three important heuristics that we're looking at. We have variable selection, value selection, and inference. And in variable selection, we are using the following strategy. So we first say we use minimum remaining value heuristic. Now, if this heuristic gives us a tie, so we can't decide which variable we're going to choose based on this heuristic, then we apply the degree heuristic. And if there's a tie again, then we choose a variable with a smaller, lower index between the ones where there's a tie. Okay, and then in value selection, we do something similar. So we say we use the least constraining value heuristic to decide which value we assign next. Now, if there's a tie, we choose the value number 3. And if we cannot assign value number 3, then we choose the lowest value possible. And for inference, we use forward checking as inference. And if we find an inconsistency, so if we notice, or if our forward checking algorithm notices that the assignment cannot be fulfilled, then we should backtrack. So we'll see an example of that in a second when we perform the algorithm. Okay. Yeah, somebody asked what is smaller, lower index. So this basically means if you have a choice between variable v1 and v4, then you choose variable v1 because it has the smaller, lower index. All right, good. Then let's start. So our first step always when we perform a backtracking search by hand is we start with step 0, which is basically the initialization step. And in this case, our assignment is empty. So we use this symbol for empty set to show that we have an empty assignment. And we write down the domain size for each step and the degree of the variables. And on the bottom right, we see the problem again, that we always have it in front of our eyes and that we can just look at the graph every time. Okay, domain size, we already determined in the first problem. All variables have a domain size of 3. And degree, we've also determined in the first problem. We've had these degrees, basically. So essentially, this is what we've wrote down here on this slide. Okay, so we start with step 1. And the first step, again, if we look back, we say we have to first do a variable selection. So we have to decide which of those 5 variables we're going to choose next for our assignment. So we use the minimum remaining value heuristic. So minimum remaining value means we choose the variable with the smallest domain size. In this case, we can see all variables have the same domain size, so we have a tie. So what we do next is we use the degree heuristic. So if we have a tie, we use the degree heuristic. So we choose the value with the highest degree. And in this case, this is variable v3. So we have determined which variable we're going to assign, v3. We're going to assign that. And now the next step is value selection. So again, we say we're going to use least constraining value as a heuristic first to decide which value we're going to assign for v3. And now if we take a look at the graph on the bottom, so here's v3. We can choose between value 2, 3, and 4. And least constraining value basically means that we choose the value which rules out the fewest number of values for the neighboring constraints. And now if we take a look exactly, it doesn't make a difference which value we choose. In any case, we will rule out the same number of values for each of the neighboring variables. So if we choose 2, we're going to rule out 1, 2, 3, 4. If we choose 3, we're going to rule out 1, 2, 3, 4. And 4, we're going to rule out 1, 2, 3, 4 variables for each of the neighboring values. So we have a tie again. And then basically, wait, I have to get my pen again. So if we have a tie in value selection, then we say, okay, we choose number 3. So we say, okay, if there's a tie, then we assign value number 3. So we're going to do that. We're going to assign value number 3. And then take a look at the domain sizes. So if v3 is number 3 value, then we have to strike away number 3 here, 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 and here. So we reduce the domain size of the neighboring values by 1. The reason why we do that is because we use forward checking as an inference. So what forward checking does is we check all neighboring values. So we have 4 neighbors of v3, and we remove the conflicting constraint. We remove the conflicting values of the neighboring values of the neighboring variables. Yeah, and we look at the degree of the different variables after we have assigned this value. So we see that v1 is only involved in 2 constraints. Why is it only involved in 2 constraints? Because we actually have 1, 2, 3 here, but in fact, the degree only considers constraints to variables that have not been assigned yet. So unassigned variables, basically, and unassigned variables are just v2 and v5. Okay, so I'm going to remove this here again. So the same is for v2. If we look at v2, v2 is only involved in a constraint with v1. We don't have to consider v3 anymore. So every time we assign a variable, we don't have to consider that anymore in the domain size and degree. So we make this dash here, basically, because we just can ignore it. And we have 1 and 2. Okay, good. Then we finish with the first step. And the next step is that we start again with variable selection. So variable selection means we again have to decide in the second step which variable are we going to assign next. So first thing is we use the minimum remaining value heuristic. So we have to check the variable with the smallest domain size. Smallest domain size, in this case, we see all variables have the same domain size. The domain size is 2 for all variables, so we have a tie. Then we go back again, we check. So if there's a tie, we use degree heuristic. Degree heuristic, we see that variable 1 and variable 5 have the same degree. So the maximum degree is 2. So it has to be one of those 2 values, variables. It has to be either variable 1 or variable 5. And then we said if there's a tie in the degree heuristic, we choose the variable with a smaller lower index. So if we have to choose between variable 1 and variable 5, we choose variable 1 because it has a smaller lower index. Okay, so we choose variable 1. And we decide again which value we select. So we use the least constraining value heuristic. If we look at the domain of variable 1, we see only 2 and 4 are left. So we can only decide between assigning value 2 and value 4. And yeah, so what we see is that both values rule out the same number of values for the neighboring. So if we choose 2, then we have to remove 2 here and 2 here. And if we choose 4, we have to remove the 4 here and the 4 here. So we have a tie again in the value selection. And yeah, then we check what we have to do next. So if there's a tie, we have to choose number 3. We can see that we cannot choose number 3 because number 3 is already removed from variable 1. And then we say, okay, we choose the lowest possible value. So the lowest possible value we can assign for variable 1 is number 2. So we assign number 2. And then what do we do next? We do again inference. So we do forward checking again. And we check all neighbors of variable 2 that have not been assigned yet and see what happens. Okay, so yeah, 1 second, I have to get my pen again. All right, so we see that, yeah, if we start with value 5 here, so we see we have to remove the 2 from here. So v5 has a domain size of 1. Then we continue with the next neighbor, which is v2. and we see we have to remove the 2 from here. And we also have to remove the 4 from here. Why do we have to remove the 4? Because we see the constraint is v2 equal to v1 plus 1, v1 plus 1. So if v2 is 4, then v1 would have to be 3, because 3 plus 1 is 4. And then basically this value for v2, so v2 equals 4, is not an admissible value anymore, so it's not possible. So we have to remove this value. So our domain size here is 0. Then we can ignore v1 and v3 because they're assigned already, and v4 stays the same because it's not involved in a constraint with v1. And as for the degrees, we can also continue, so we can ignore those. We have a degree of 0 here because it's not involved in any constraints anymore. And we have a degree of 1 for those 2. So now, one important thing happened. We see that we have a domain size of 0 here. Now, what that means is that our inference, or our forward checking, detected that this is an assignment that doesn't work. So as soon as we have reduced a domain size of a variable to 0, we have detected a failure in our backtracking search. So we can write that down here. Backtrack. So I'm going to write that down on the side every time we detect such a case where the domain size is 0. And this means we have to backtrack to step 2. So what that means is we have to go back to step 2, in which we are anyway in currently, and we have to try another value for v1 because we found out that v1 equals 2 just doesn't work. So it just will result in a failure for the whole backtracking search because we don't have any value anymore left to assign to variable 2. Okay. So yeah, then I'm just going to do one more step because then the time is unfortunately up again. So we're just going to do step, oh, sorry, it's not step 3. It's basically step 2. So every time we backtrack, we have to repeat the step again. That's why we write down step 2. Okay, so then we have to take a look again. We have to reassign variable 1 because we said 2 doesn't work. So as you can see down here, we tried out variable 2. So next we have to try out variable 4. So we choose v1 equals 4. Yeah, then I have to remove this here again. Yeah. Oh, sorry. So like that. Okay, so if we want variable 1 is equal to 4, we have to perform forward checking again. So we have to check all possible neighbors again of variable 1. So I'm going to remove this here again. Okay. So again, we start with a variable 5. So there we have to strike out 4 in this case, because if v1 is 4, v5 may not be 4. So again, we have 1. We can ignore these 2. Then we have to check variable 2 again. And we can see that if v1 is equal to 4, then we have to check this constraint again. So we see that the only value left basically is 2 in v1. So we have to see if 2 plus 1 equals 3. And we see that v2, there is no value that equals that's possible anymore. So we have to strike away 2 and we have to strike away 4. And this means that again, our domain size of variable 2 has been reduced to 0. And v2 doesn't change because it's not involved in the constraint. Then we write down the domain sizes again, the degrees again. This is basically the same as in the previous step. And again, we see that we have the case that our forward checking algorithm has detected a failure. So we can write down again backtrack. And now to which step? So since we have tried out all possible values that we have, or all remaining values for variable 1, we have to actually backtrack to step 1 again. So this means yeah, exactly. Somebody wrote it in the chat. So we have to backtrack to step 1 again because there are no more possible values that we can try out in step 2. Okay, so yeah, since I see unfortunately that time is up again, I think we're just going to make a break here. So we're going to just stop here and continue at this step. So basically at step 1 would be the next step that we have to reassign. We would continue next week again. Then thank you all for joining today. So basically the exercise session is up and we'll continue next week. And I'll just, as always, stay here again to answer some of the questions that you might have. And yeah, Dao-E, I think you can stop.